guys, Mr. Shaw here. I'm in the kitchen today because today we're going to be taking a look at the rock cycle. We've talked for the past couple of days about minerals and the ways that little granules of solids can compound themselves and combine themselves to make rocks. We've learned about the properties of those rocks, how some rocks are harder than others and you can scratch them to be able to tell. Some rocks have different colors, some rocks have different textures, they break in different ways. So today we're going to be looking really deeply at how these rocks form. And we can look at this in nature, and we will look at this in nature, and we have looked at this in nature. But one of the easiest ways to understand this is actually in the kitchen. So we're going to do a quick tour of the rock cycle using some things you might have lying around the house. Feel free to experiment with some of this at home if you have these materials around. Before we actually go into the experimenting, let's go ahead and take a look at what we have. The rock cycle always starts off on the surface, and it starts off with something called sediments. Sediments are basically just tiny little bits of minerals or rock that have been broken down through two different processes, weathering and erosion. So weathering is when you have any type of water, whether it's rain, ice, snow, sleet, falling down from the sky, breaking apart rocks into bits. You also have wind that does this, because wind can carry small bits of sediments and can actually batter against rocks and break them apart. And you can have ice do this inside the earth as well by freezing and cracking the way you make a pothole. Depending on how much weathering takes place, you've got a couple of different types of sediments that form. The smallest is clay. I've got a little cocoa powder here. And the clay sometimes is really thick and like clumped together, and sometimes it's really, really soft and tiny. Depends on how much water is in it, because water can hold the clay sediments into clumps and clods, but you mess around with it a little bit and you realize these are the tiniest sediments you can have, almost microscopic, to the point where it looks like it's on my hands and like almost a liquid because it's so small. A little bit larger, usually sediments that don't get broken down as easily, are silt. Silt makes for some really good soil, and in healthy soil you can find a lot of these like medium-sized sediments. Silt is often on riverbeds, kind of gets washed up on shore, has a lot of minerals in it that are good for plants to grow. Now this is just sugar, but one of the most common forms of sediments that we'll see is sand, which looks a lot like sugar, but more of a tan color. However, sand can come in all kinds of different colors. You can have sand that's black, white, green, orange, red, every color, because it depends on what kind of rock gets weathered down into little bits. Same thing is true of silt and clay. While we most often think of clay as sort of orangey red, you can have clay in different colors, depending on what's getting broken down. But some things don't get broken down as easily, and so you tend to find them in other types of sediments. Quartz is an example of a mineral that doesn't really get broken down very easily. It's what makes up a lot of our glass. And because quartz is so hard, I think it's a 7 on the hardness scale out of 10, it tends to stop at the level of sand. It doesn't really get broken down further because most of our natural weathering processes, wind, water, ice, they can't break down quartz that much. Finally, the largest one is gravel. I have these caramel M&Ms. I don't really like the caramel M&Ms that much. They're pretty good. I clearly ate most of them, so it doesn't really matter if you dislike candy. Candy is still candy, and candy is still delicious. All 4 of these are categories of sediments. You can actually have many different things in between these, but we kind of organize them according to their size because that lets us know how much weathering has taken place. Sediments tend to be found on the surface. Slopes of mountains on the top of the ground where like a lot of rain and water might be rushing down. Deserts where there isn't really a lot of plants growing, so the sediments are just exposed to the wind. And we tend to find the most weathering happens there because the sediments that are on the ground are totally exposed to weathering. Now, the second process that I listed, erosion, is when all of these sediments that are getting battered and mixed around get carried together so that they can be set down in a place. And that takes us to our second stage of the rock cycle, deposition and cementation. Eventually, all of these sediments can get carried to one spot by wind, by water, by rivers, by whatever forces of nature are bringing them together. And this usually happens underwater. Riverbeds and ocean floors are the most common places where you'll see this. As these sediments start to collect, they usually settle in a particular order, which you can see here, with the smallest sediments and the largest sediments kind of going in layers. Small sediments can kind of fit between the cracks of the larger sediments, and even if I add more of these big things in here, and then I add more small stuff in there in a different order, the small sediments, when they get jostled around a little bit, tend to sink to the bottom, with the largest ones being on top. Now, this is called deposition, but that alone doesn't make a rock. Right now, I just have a pile of crap, and it's not really stuck together in the form of a rock. To stick this stuff together and make it into a rock again, we have to go to the second process, cementation. Cement, you may know, is what's in concrete in our sidewalks and some of our driveways and roads. And concrete basically just sticks a bunch of little pieces of stuff together, mostly sand. Well, that happens in nature as well. And there's a lot of different chemicals that can cement things together. But for sake of time, I'm going to use a chemical I have in the kitchen, some jet puffed marshmallow cream. Now, we're going to make a little Rice Krispie treat to represent our sedimentary rock. So I'm going to have some marshmallow cream. I'll add some sediments to it as well. And usually with a sedimentary rock, the cement is so strong, usually found from chemicals in the river, that you don't really need any other forces like pressure or heat or anything else. The cement sits there for a long time, kind of weaving its way in between all of the different sediments, getting them stuck to each other. Some sediments will still keep flowing. If you go to the bottom of an ocean, you might find some rock underneath all the sand, but not all the sand has enough time to stick with the cement. And of course, there's ocean waves still kind of flowing and waving. And so those will carry some little bits of sediments as well. To actually stick there, you need a long amount of time and a little bit of luck before it can make a rock. And that rock has to sit undisturbed for a while so that the cement can really have time to harden. All right. So we've got the beginnings of what will eventually be a sedimentary rock. It's still pretty flexible. A lot of the sediments can easily be removed, but with some time, we'll end up with a sedimentary rock. Now, once this rock forms, it's deposited at the bottom of a river or an ocean. More and more layers of sediments will get buried on top of it. All of these little grips, which is very difficult for me to deal with because of my sticky hands, these little sediments, these little Rice Krispies, these little cocoa powders, they're all going to end up on top of this. And eventually there'll be so much stuff layered on top of it, it starts to press down. And that's pressing down due to the force that Earth puts on all of its objects, gravity. That pressure leads us to our second type of rock. These sediments cemented together make sedimentary rock, but when more and more of those start to press, we get what's called a metamorphosis. Sediments end up on the bottom of the ocean floor, but they get buried under more and more layers of sediments on top of it. Eventually, you have so many layers of sediments that they start to press down. And that leads us to our next phase in the rock cycle, metamorphic rocks. Say I've got this sedimentary rock right here, Grahamstone. And Grahamstone is at the bottom of the ocean floor. It's turned into a rock, awesome, but more stuff is going on in the planet. And over time, another layer of rock forms on it, Chaco Rock. Chaco rock lays down on top of it, cements together, turns into another sedimentary rock, and then yet another layer over millions of years forms on top of it. Marshmallow mineral. I'm coming up with these names on the fly. Clearly, I have no idea what I'm talking about. I've got my Grahamstone, Chaco rock, and marshmallow mineral on top of that. These layers of rock continue to press down on each other because there's always gravity, and rock is really heavy. So rock pressing on rock, pressing on rock, pressing on rock will eventually form a new rock that has combinations of all the minerals that it's part of. Now, the pressure alone usually isn't enough. These things tend to be buried deep underground, under mountains and under deep rock, and they get so close to the center of the earth that they actually get exposed to the heat under the earth. Now, they don't get melted. It's not so hot that these things will actually melt down into lava or a magma or some other kind of molten rock. Instead, what you have is just enough heat that it can start to change the shape of the rock. If you imagine holding a ball of clay or Play-Doh in your hand and you keep messing around with it, the heat from your hands, along with you pressing on it, ends up changing the shape of the clay. Ice cold Play-Doh that's just out of the fridge or freezer, I don't know who refrigerates their clay. That won't really change shape as much. But with a little bit of heat, because our hands are warm, that's really what does the trick. So you combine the pressure along with the heat without setting the marshmallows on fire or the Chaco rock getting totally melted, and you end up having something where all of the layers are kind of stuck together and can change shape. Now, I'm going to let this heat up for a little bit, but inside of the earth is our core. We're going to learn more about the layers of the earth in 2 weeks from now, but the thing to know is that underneath the crust that we're standing on, the layer of rock that all of us live on, are 3 more layers. Underneath us directly is the mantle. Now, this is many, many miles deep from where we are, but you can see what happens when the mantle comes out onto the crust when a volcano erupts. When a volcano erupts, the lava and magma that's underneath the crust spills out onto the crust and then cools back into a rock. Well, all of that stuff is underneath us, and if you're really close to it, you're going to feel that heat. So when rocks get buried really deep and get really close to the mantle, they start to feel that heat as well, which is represented by the flame underneath this plate. It's not actually touching the flame, it's not actually going to melt itself, but you can even see in this s'more that we're starting to change shape a little bit. The marshmallows are starting to get a lot flatter. I just broke this thing, so you've got a little bit of a change shape. Instead of being totally flat, you have sort of an angle to it. Even the chocolate that's here is starting to lose some of the shape that it once had. This is why we call it metamorphic. Morph meaning changing shape. And as this happens over a long period of time, even the graham cracker layer, which is much harder, might change shape. Now you can tell that each one of these is changing shape at a different amount. Obviously the chocolate is going to change shape the most, the marshmallow will change shape kind of a medium amount, and then the graham crackers are going to change shape the least. The same thing happens in nature. Just like different types of sediments get weathered to different amounts depending on what they're made of and how hard they are, different materials will get shaped a different amount depending on what material they are or how hard they are. These different properties of these minerals help scientists figure out what used to be in an area over time. Now, eventually, you get to the point where something gets so deeply buried that it actually starts to melt. Man, my stovetop is dirty. Sorry, y'all. I've been doing a lot of cooking just right now. When this melts, it turns into something called magma. Magma is found in the mantle of the Earth. The inside of our Earth is so hot inside the core that it can actually melt iron and metals and steel. But the mantle is not as hot, and it mainly just melts rocks and things like that. It takes a lot of heat in order to melt rocks themselves. And so you can see in here, I've got some of the Chaco rock, as well as these gummy rock, bearstone, let's call it bearstone, mineral bears, whatever. So as these get melted, because they get so hot, they turn from a solid to a liquid. Just like ice melts and turns from a solid to a liquid, the same thing happens with rocks, but they have to get a lot hotter. Same thing can happen with anything solid. Metal, glass, all of these things can melt exposed to enough heat. You can see already that the color of this chocolate is starting to change. The color of the gummies is also starting to change, and it's starting to lose its solid form. Once something gets so hot that it starts to melt into magma, there's a couple of different things that can happen. It could cool back into rock under the surface of the Earth. It could just get far enough away from the mantle that it starts to cool down. Or it could erupt in a volcano and cool up on the crust. When it cools under the Earth, the liquid under the Earth is called magma. But liquid that is above the crust, we call that lava. Basically the same thing, it's all melted rock, but we have different names for it depending on where we find it. The reason this matters is because when it's above the crust, it cools really, really fast. You tend to find igneous rocks with a lot of bubbles, like what you see in these gummy bears. These bubbles, when they cool fast, keep their shape and turn into basically just holes in the rock. You also tend to see a lot of crystals, like you can see the sugar crystals forming on the outside of the chocolate. Those sugar crystals you can find inside rocks like granite, where if you hold it up to the light, you can see some shine to it. We looked at some of this on Monday. Another thing you'll find is sort of a glassy, smooth texture. You can see that these little chips of chocolate are starting to lose their shape, and they'll end up having a much smoother texture with some time. I can make this a little faster if I actually simulate some of the processes that happen underneath the Earth. Of course, as these things move and change shape, they'll change much more quickly than a metamorphic rock. Metamorphic rocks just have to be pressed over a long period of time, but when you melt something down like this, it can become completely different in its shape, color, and texture faster than anything else. Now, this is disgusting, but nonetheless, shows you what's possible with an igneous rock as it starts to cool. So let's go ahead and turn off the flame now that we've got this oozing bubbling and see what happens when this starts to cool. To cool this quickly, I'll move it off of the heat source completely because we're going to imagine that this is actually like a volcano. It's erupted, and it's moved to where it's going to cool into rock. All of this bubbling lava that you see, it was going to either start to dissipate and settle back down if it cools slowly, or if it cools really quickly, it'll turn solid really fast. One way or another, you look inside the rock to find evidence of what was there before. Are there crystals from things that cooled really quickly? Are there bubbles? Is there a smooth, glassy texture? This is what we can find in an igneous rock, and a lot of lava that erupts will look really similar. Let's go back to our metamorphic rock, which didn't get so hot that it melted. Nonetheless, we can kind of see that the chocolate has started to change shape. It's still solid, but kind of cool in some areas, and it definitely no longer has that rectangle to it. The marshmallows haven't changed shape as much, but now if I press down on them, they don't totally bounce back to the way they used to be. They're starting to get a little flatter. In a metamorphic rock, you tend to see layers like this, where you have different types of layers of rock that are sort of bendy and wavy because they've been shaped by the gravity of pressure on the earth. And then finally, we'll go back to our sedimentary rock, most of which I had to eat because it was stuck to my hand. And at this point, the sediments don't peel off as easily. They're cemented together pretty solid, although there are still many sediments on the ocean floor waiting behind. This is our rock cycle, starting with sediments on the surface that get weathered and broken off and then carried through erosion to places underwater where they get deposited, cemented together by chemicals inside the water, turning into sedimentary rock, then pressed down with pressure from gravity of the layers that bury it above it, and then heat from the middle of the earth to turn into a metamorphic rock. And finally, when it gets pressed so far deep that it starts to melt into magma, it can erupt or cool under the crust to turn into an igneous rock. The cycle can go in any direction, any order, but these are the processes that you can expect.